last time we met, we talked about how to graph points, but we didn't talk about how to graph actual curves, so that's what we're doing today. So some of these are kind of basic. I want you to think about a t-table for a lot of these when you're graphing them by hand, and then we can talk more about how to graph things on the calculator. So basically, if you have r equals 2, so I say on here that theta is the independent variable. In other words, think of theta as the thing that you're plugging in each time. So I'm going to put theta in r, even though it's going to be, you know, your points are always r comma theta. So if I have r is equal to 2, that means r is always equal to 2, no matter what my angle is. So I could have an angle of 0, I could have an angle of pi over 6, pi over 4, pi over 3, right? I could go to 7 pi over 6. Any of those are going to have a radius or an r value of 2, okay? So that means going along the line, right? Remember how we did this yesterday? Going along the angle of 0, we would go out 2 units along there. So we're going to be here. Going along the angle of pi over 6, we would be out 2 units. Going along pi over 4, we're out 2 units. Do you see what shape we're going to get as we're doing this? Not a spiral, a circle, because it's your radius is always equal to 2, right? The r value is always equal to 2. Do you guys know what the rectangular equation would be? Like if I only had x and y? Yeah, x squared plus y squared equals 4. Do you guys remember that from geometry? We also did a little bit of math for 2. It's x minus h squared plus y minus k squared equals r squared. Yeah, so r equals 2 in polar coordinates is equivalent, maybe I should write that, equivalent to x squared plus y squared equals 4 in rectangular. And we'll talk about that later as well. All right, so now this says, well, what if your theta is equal to pi over 4? So it's saying theta, your input is always pi over 4. Well, that's kind of weird to think about. So if your input's always, 3 pi over 4, I think I said pi over 4, 3 pi over 4, that means your radius could be 0, it could be 1, it could be 2, it could be 3, it could be negative 1, negative 2, negative 3. But your angle is always 3 pi over 4. That's what we're saying. So if I have 3 pi over 4 comma 0, that's at the pole. 3 pi over 4 comma 1, that's going to be right here. 3 pi over 4, 2, 3, 4, 5. But you also have negatives. Remember, negatives go back in the opposite direction, so we'd be here, here, here. Oops, I missed it. I'm on the wrong line, aren't I? The middle line. So I'd be here. So what do we end up getting? Yeah, just a line. So think about that line if I was just in the xy coordinate plane. The line that's directly in the middle of quadrant 2 and directly in the middle of quadrant 4. What line would that be? Y equals, so think about the y equals mx plus b. What's your m? Negative 1, right? Negative 1x, that's it. Okay, so we're going to be talking about how to switch from rectangular to polar and polar to rectangular. But this is kind of a little preview. All right, so what if we have 3 sine of theta? Okay, this is where it gets to be a little bit harder. So I still want you to think about different angles. So we can do like 0, pi over 6, pi over 4, pi over 3, but you're going to have to do a lot of these. Okay? So if you have 3 sine of theta, if you plug in sine of 0, what is sine of 0? Everybody know? 0. So that means 3 times 0 is 0. What is the sine? Come on, smarty pants. What's the sine of pi over 6? Uh-oh. I heard you before class saying, I have to memorize the unit circle again. It's 1/2, yes.
You should already know it.
So you have 3 times 1/2, so 3 over 2 is really the same as, I'll use a decimal, 1.5. Well, what if I have pi over 4? Here's where it gets a little bit hard. You might want to use a calculator. Pi over 4, its sine value is root 2 over 2, so you have 3 times root 2 over 2. Root 2 over 2 is around like 0.7, so you're going to have around like 2.1, right? And then pi over 3, what's its sine value? Root 3 over 3. Or root 3 over 2. Root 3 over 2 times 3. So when you take that times 3, so do 0.866 times 3 for me. What do we get? You have to do it. 0.866 times 3. 2.6, somewhere around there. So that's when, if you're getting a lot of these like square root answers, square root of 2, square root of 3, and so on, I tend to just think about the ones where sine comes out nice. Okay, sine was nice for pi over 6. Sine was nice for pi over 2, right? What's the sine of pi over 2? 1, right? So we get 3. So we're going to have 0, 0, so that's the pole. We're going to have pi over 6, comma 1.5, so, or well, 1.5 comma pi over 6 is how we really read it. So that means go along the pi over 6 line, this line, and we're going to go out 1.5. So if you go over 1.5, you're right here. Do you guys all see that? And then we have pi over 4, 2.1. It's a little bit bigger than 2. And then we have pi over 3, 2.6. So we're still getting a little bit bigger. But then all of a sudden pi over 2 is at 3. Okay? Is that as big as we're going to get, you think? Can it go to like 6, 7, 8? No, because what's the biggest value that you can ever get out when you take the sine? Sine of whatever gives you what? What's the biggest value you can ever get out? 1, right? Sine is always between negative 1 and 1. So the biggest that you're ever going to get is 3. And that's happening at pi over 2. All right, so we have that. All right, then we start to sketch the rest of it. So if you plug in more of these points, sometimes you have to do a really long t-table. So let's say we plug in like, let's do, I'm trying to think of like nice ones. Let's do 5 pi over 6. 5 pi over 6 gave us what? Sine of 5 pi over 6 is 1/2. So we get 3 over 2, which is still 1.5. So we're right here again. Do you guys think that this is symmetric? It's going to be the same as the ones that were over there? Yeah, because the sine values are all the same for those. Whoa, I did not meet that right. So it's going to look like that. So the question is, well, what if you continue into the third quadrant and fourth quadrant? So what if you do, here's where it gets a little weird. So what if I try 7 pi over 6? What will that give me? Close. Not 1.5 though. Negative 1.5. And then how would we graph that? So we'd go along the 7 pi over 6 line, which is here, but we would go back 1.5. Wouldn't we just be starting this curve over again? Do you guys see it? So once you get that it's starting over again, you're good. We're done. You don't have to do any more. Does that make sense? So I do have a couple like this on your homework, so I just want to kind of show you, if you're lazy, and I understand you guys have a lot of homework, you could do all of this by hand, right? You can do this. You know your unit circle values. I feel confident that you guys do. But if I ask you to find a whole bunch, I think I give you a whole table that you have to fill out. Then go to second table and fill things in. So do 0, right? Pi over 6. Oh, we have to do, hang on, this one. You guys already have it, so your table is set so you can ask. But if you have to, you do second table set and then auto ask. And then go to your table. So you can put in whatever you want. So you can put in 0. You can put in pi over 4. And you should be getting those values. Do you guys see? Pi over 4, 2.1. So do you see how that's going to make your life a little bit easier on your homework? Are you glad I told you that? Okay. I know, you weren't paying attention. Now you lost it. Too bad. All right, so next one, 2 cosine of theta. So if you have 2 cosine of theta, again, you can do the same kind of thing. So you're setting it up with your theta and your r. And you're just plotting points, right? You're plugging in 0. You're plugging in, think about what the nice things for this one will be. Pi over 3, right? Pi over 2. 2 pi over 3. Pi. So let's try those, see what we get. So when you plug in 0, cosine of 0 is 1. So we're out at 2. Pi over 3, what's cosine of pi over 3? 1/2, right? 2 times 1/2 is 1. So along the pi over 3 line, I'm only going to go out 1. Pi over 2, cosine of pi over 2 is 0. So I'm back at the pole. 2 pi over 3. 2 pi over 3 is going to give me negative 1/2. So times 2 gives me negative 1. So along the 2 pi over 3 line, which is right here, you're going to go backwards 1, which is going to put you right there. And then pi, cosine of pi is negative 1. So I get negative 2. So along the pi line, I go back. So here's the pi line. I go back 2. Do you guys see how that takes you back to this point right here? Okay, now it's still kind of hard to tell what that shape is. So if you need to do some of those intermediate points like pi over 4, pi over 6, and so on, you can. It ends up being a circle. So it's a circle right here. Okay? So one of the sides is on the pole and one of the sides is at the x coordinate, like 2, 0, the xy coordinate 2, 0. All right. So I had you at the beginning of class fill in all these pictures. We're going to verify if your pictures are right. You ready? Do you have these pictures? And we're going to talk about some important points on these pictures. So make sure you're filling in these certain R values. So the first one goes out to 3. Okay, the second one looks kind of like a 4-leaf clover. It also goes out to 3, back to -3, and so on. Up to 3, and down to -3. Okay. Do you see where the 3 is coming from? Yeah, it's the number out front, right? The next one, we still go out to 3, but now there's only like 3 petals. But previously we had 2 petals, right? We had that 4-leaf clover.
Does the 2 have any? Does the 2 play a factor?
The 2 does play a factor. So look for a pattern in these pictures. So anytime we had 2s, we ended up having 4 petals, right? Anytime we had 3, we had 3 petals. Anytime we had 4, we had, do you guys see the one with 4 theta? We had 8 petals. When we had 5, we had 5 petals. When we have 6, we would have 12 petals. When we have 7, we would have 7 petals. What's the pattern? Yep, so it says, if you have r equals a times cosine of n theta or r equals a times sine of n theta, it creates a rose, like roses, we call these roses, like flowers, with 2 n petals if n is an even number, and n petals if n is an odd number. The number a adjusts the length of each petal, right? So if the number out front is 3, you're going to go out a length of 3. And you even do that like here. This length right here is 3. Does that make sense? They're all going to be like 3 units long. Okay, so let me pause it really quickly so you guys can go and break. All right, so those are the rose curves. Do you guys understand the rose curves? They look like little flowers. If you have an even number, like a 2n, an even number, you get 2n petals. So if you have like a, let's see, like cosine of 5 theta, that's not an even number, right? 5 is not even, so it's odd, so there would be 5 petals. But if you had cosine of 6 theta, you would have 12 petals. There would be a lot. Okay, does that make sense? You guys all understand the rose ones? Yes. All right. So the next type is called a lemniscate.
It looks like a peanut.
Yeah. I think it kind of looks like an infinity sign. So that's what the blank is for mine, which look like infinity signs.
Wait, so you're not supposed to put the negative in parentheses? The negative is not being squared, it's just the 3. Yeah, how do you go?
Yeah, it's like, so basically if you're trying to graph this, so when you have r squared equals -3 squared cosine of 2 theta, when you take the square root of both sides, you need to do a plus or minus, right? So it breaks into 2 things that you're going to put into your calculator. So the first one is going to be like R1, I think I wrote Y1 earlier, R1, which is going to be positive square root of negative, basically 9, right? -3 squared cosine of 2 theta. And then the other one is going to be graphed as R2 equals negative on the outside and then -3 squared.
So
-3 squared cosine of 2 theta.
square the negative?
No, because it's only the square is attached to the 3, but not like there's no parentheses there. All right, so when you sketch each of those, you get these. What do you guys notice about the cosine ones? What do you notice about the sine ones? Cosine is straight up and down, right? And it goes to a height of 3 and down to -3. And this one goes to a height of 5 and it goes down to -5. Okay, so that's why I left it as something squared so you can see what those numbers are. Ben. Every day.
Been there, done that.
Yeah, all right. So next one. So when you have the sine, it's kind of on that like 45-degree angle or 135-degree angle. But it's the same idea. It's just this distance right here. That distance is 5. This distance, right, is also 5. Same here. This distance is 3. Does that make sense? So you're still going out the same amount. All right, do you guys have all those? Can I go to the next page? All right, can you guys all say lemniscate? Lemniscate. I hear lots of math teachers pronounce this wrong. It's all right. Lemniscate. I don't know. Whatever. It drives me crazy. All right, the next one is limacon. Yes, Kyle.
What does it mean by
Make a hypothesis. Make a hypothesis on what you think the curve looks like. What did you guys think the last one looked like? Those infinity signs, right? What do we think these ones look like? Huh. Kind of weird. Yeah. So some of them are circles, right? Kind of like circle-y. Some of them have a little loop in them. Okay, so these limacons, basically, if there's, so as you set it up, if you have, so if I had 5 plus 2 sine of theta, let's say I had that. Okay, A would be 5 and B would be 2. So what we're saying is if A is less than B, there's what we call an inner loop. But if A is greater than B, there is no loop. Okay, and these numbers are going to tell you exactly how far out you're going to go along the axis. So for sine, it's going to go along the y-axis. So if you look at this one, for example, the r equals 5 plus sine of theta. The A and the B are 5 and 1. Do you guys see that? What happens when you add A and B together? You get 6. Do you see that on your curve somewhere? It goes up to a height of 6. What happens if you do the B value, well, yeah, the B value minus the A value? You get -4, right? You do 1 minus 5, you get -4. Does that make sense? So do you guys see those two numbers represented on your circle? You got it? All right, so basically if A is less than B, so if I had, so this would be one where if I was trying to do a rough sketch of what this one would look like, the highest point it would go to would be 7. What's the lowest point it would go to, guys? -3, right? And then you would just kind of have a circle-y shape in between there. Okay, and since it's sine, it's along the y-axis. Alex, stop. All right, so the next one, so if I get r equals, so let's say I had 3 plus 4 sine of theta. Okay, this is one where your A is 3 and your B is 4. So A is less than B, right? That means that there is an inner loop. So if you were going to sketch this one out, what you would do is you would have A is 3 and B is 4, so you would add those together. You'd go up to a height of 7. And then when you do 4 minus 3, you get a 1, right? Do you guys see? So you're adding them together. So you're doing A plus B, and you're doing B minus A. So what's going to happen is it's going to look like there's a little, do you guys see how I drew it? A little like loop in there. And that loop goes up to a height of 1. Do you get it? Do you think you could sketch that? All right. So those are called limacons. So the next ones are very similar to the limacons, and I always hate trying to tell the difference between them because it's like, ooh, is there a little loop? Like, look at the second one. Doesn't look like there's a little loop there, but there's not really. These are called cardioids. Think about why it's a cardioid. What stem do you see in that cardioid? It looks like a heart. Not like a pointy, oh, happy Valentine's Day, I love you heart, but like an actual human heart, which is not like pointy on the bottom, right? You know what I'm saying? So it looks like a heart. So don't draw it like a Valentine's Day heart. All right, and do you guys see what's different about this one? What makes it not a limacon, which technically it is kind of a limacon?
The A and B values are the same.
Yeah, the A and the B are the same. So if you subtract those two, you get a 0. So your loop is like of size 0, basically. There is no loop. Okay, instead it just kind of goes to a little point there. Okay, do you all see that? So same kind of thing. All right, and then the final thing are the spiral of Archimedes. Yep, Archimedes. You guys all know Archimedes, right? You guys know any fun stories about Archimedes? Yeah? He ran naked through the street screaming what?
Eureka.
Eureka, that's right. Because he was in the bathtub and the king had thought someone was stealing from him basically and creating these crowns for him that were not made of gold. So he was giving them the gold to make the crown, and then they were mixing it with something. And so he was in his bathtub thinking about, wow, I got to solve this problem for the king. And the water is displaced as he's getting in the tub, and he realizes, oh my gosh, I can see if I sink a certain amount of gold, it's going to displace the same amount as his crown, blah, 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 blah. And then he figures it out and runs naked through the streets. That's the story. There's lots of stories. Mathematicians are very strange. You should do some math history. All right, so graph the following curves and make a hypothesis. So we have r equals theta, we have r equals 2 theta, and we have r equals 5 theta. They're basically the same thing. It's just a spiral. It starts at the pole, kind of wraps around. Okay, but the difference is that the bigger number you have in front of theta, the more spread out your spiral is. These all go on forever, though. Okay? So they get bigger and bigger and bigger. So that's the spiral. All right, so let's see if you guys can do this. These are the types of things that are on your homework. So it says complete the table and plot the corresponding points. Use more points as needed. Okay, so if you're doing these, so if you plug in pi over 4, cosine of pi over 4 was root 2 over 2, right? So like I told you on your homework, if you want to cheat a little bit, I will not judge. You can put in 3 cosine of theta, and then go to your table and plug in pi over 4 for the first one, and then plug in pi over 2, right, and so on. So go ahead and do that on your table.
How do you get to the table?
Second graph.
Yeah, it's about the graph.
How do you,
So if you can't change it, then do second table set and make it so your independent is on ask. Yeah. And I'm really just doing this because a lot of you guys don't know what like root 3 over 2 is off the top of your head. You would use your calculator anyway, so I might as well show you how to do this on the calculator. So we get these different values. So 2.1, 0, negative 2.6, negative 1.5, and 3. Did you get all those? All right, can you guys repeat those back to me in just a second as I close out of here? Maybe I can kind of put it to the side here. Let's be tricky. Oh, yes, there we go. All right, so I have 2.1, 0, negative 2.6, negative 1.5, and 3. That looks like negative 26. Okay, but the hard part is you guys got to know how to graph these points. That's what we did last time. So do you all know how to graph these points? So you go along r equals pi over 4, and you go out 2.1. So it's going to be a little bit more than 2. You go along the pi over 2 line, and you go out 0. You go along the 5 pi over 6 line, which would be this line right here, and you go backwards, negative 2.6. And then you go along the 4 pi over 3 line, which 4 pi over 3 is like 1 and 1/3 pi. It's this one right here. And you go backwards, 1.5. Okay, and you go along the 2 pi and you go out 3. Okay, so you get a series of points. And this is what makes it difficult, because if you don't know these various shapes, you're going to have a hard time figuring out what it is without graphing a whole bunch of points. Can you guys kind of tell what it is? Is it one of the infinity signs, one of the petals? What is it? It's a circle. Yeah, this is a circle. And if you want to know how far out it goes, think about the biggest thing that cosine can be. So cosine is always between -1 and 1, right? So think about what you plug in for theta to get a cosine value of 1. You plug in 0 or 2 pi, right, to get 1 out. Does that make sense? So in this case, we would have 3, because we're doing 3 cosine of theta. So if we plug in 0, we get 3. What do I plug in for theta to get -1 out for cosine? Cosine of what gives me -1? Pi, right? Like we're saying, when do I get over here on this side? Pi. So when I plug in pi, you should get -3. Okay, those actually both end up being this point over here. Okay, but that's good to check because you want to think about the biggest you can have, the smallest you can have. So it ends up the smallest value we're getting out is the 0. All right, so let's do another one. So if I have r equals 2 plus 3 sine of theta. Again, let's go to our table. And we're going to plug in those same values. So luckily I already have them on my table, don't I? So as I plug these numbers in, so I get pi over 4 gave me 4.1, pi over 2 gave me 5, the next one gave me 3.5, -0.6, and 2. So the hard part is, like, once you get those, you got to graph them, right? So you go along the pi over 4, you go out 4.1. 1, 2, 3, 4, 4.1. Pi over 2, you go out 5. Is that the biggest that you're ever going to go out? Tell me why. It is the biggest. Why? What's the biggest you have for sine? Guys, this is not a hard concept. You can do this. The biggest thing you ever get out for sine is 1. So if you had a 1 here, then you have 2 plus 3, right? That's as far out as you're going to go. You're not going to have any values bigger than 5. All right, and then 5 pi over 6, you get 3.5. So 5 pi over 6 over here. 1, 2, 3. 3.5. Would that be the same as like pi over 6? Sometimes you can use the symmetry to help you. Yeah, it's the same as pi over 6, right? So you could actually get another point over here. And this one at pi over, what were we at? Pi over 3. I went along the pi over 3 line. Nobody told me you could have gotten a bonus point. I went along the pi over 3 instead of the pi over 4 line. But the pi over 4 is going to end up being symmetric to this other one. Do you guys know what I'm talking about? Like if I have sine of pi over 4, isn't that the same as the sine value at 3 pi over 4? Does it make sense? So they end up having the same outputs. All right, what about 4 pi over 3? So 4 pi over 3 is along this line right here. So we're going back 0.6. So somewhere right in there. And then the 2 pi, we go out 2. It's like that. So we got a lot going on.
Wait, Miss Potts,
Did I mess something up?
why are you on the 3 pi over 4 line?
Oh, I was just saying like it's symmetric to the other one.
Oh.
Like it's the same as pi over 4. All right, so this is a weird one. This is where knowing the shape can help you. So remember, if it had been 3 plus 3 sine of theta, that would be a cardioid. Those A's and B's would be the same. James, put it away. What do you got? Okay. Thought you had your phone. All right, I can see like under all these tables, so I can always see when you guys are on your phone. So this is not a cardioid. This is one where you have the A is equal to 2 and you have the B is equal to 3. So let's go back. If A was less than B, there's an inner loop. If A is bigger than B, there is no loop. So is A less than B? Yeah, there's going to be an inner loop. So this means that we have an inner loop. And when we subtract them, so if you subtract B minus A, you get 1. So, well, maybe I should write 3 minus 2 equals 1. That means its loop is going to go up to a height of 1. Okay, so think about it. If you plug in 3 pi over 2, let's try that. If you plug in 3 pi over 2, what do you get for sine? -1, right? So you would have 2 minus 3. So you would go along the 3 pi over 2 line, but you'd go back 1. Doesn't that put you right there? So as you're sketching this in, it's going to be very symmetric. So we're going to have this kind of like circle-y shape, but it's going to go in and do a little loop and then go back around. Okay, so sometimes you have to do a few more points to kind of see what's going on. Does that make sense? Do you guys get it? Could you show me lots of points and graph things very, very carefully? Yes. I included grids because I didn't trust that you could draw the polar grid on your own. So I'm making a lot of worksheets for this chapter. All right, so any questions on any of that?